Hi there, welcome back to the formulaic approach. Now, in this video, I briefly want to talk about chemical equilibrium, and I'm making this video because of those of you that are writing exams tomorrow, okay? Just so that you understand the context of chemical equilibrium shortly, okay? So this video is not going to be so long, but I plan to have a longer video that will explain energetics down to chemical equilibrium, okay? All right, so now where do we start from? First, what is equilibrium? Equilibrium is a state of no observable change in a chemical reaction. Equilibrium is a state of what? No observable change in the chemical reaction. I still like to give a good definition. I'm going to get to where you will understand what you are probably going to see in your exam, okay? But I want to build it up a little bit too, okay? There are two types of equilibrium. We have the static equilibrium and we have the dynamic equilibrium. Static equilibrium is where a system has gotten to the equilibrium state but does not, and remains in that equilibrium state, does not, the equilibrium condition does not change. But dynamic equilibrium is where the equilibrium is changing, but it is almost as if it is the same thing that is still there. Do you understand? The equilibrium is changing back and forth. So you already know that in a chemical equilibrium, if I have this chemical reaction to be in equilibrium, these are the arrows we use in representing them, okay? So, and of course, these arrows are of two types. We have the one where they are the two lengths, the two half arrowheads have equal length, and we have one where there's one that is longer. This one shows you that the equilibrium favors the forward reaction than the backward, and the one that goes like this, and one that goes like this shows that the equilibrium favors the backward reaction than the forward reaction. Excuse me. So that is what this is about. So, and of course, in the chemical reaction, we already have both the product side here and the product side here and the reactant side here. So the guys here, we call them reactants. The guys here, we call them the products. The products. Now, basically, let me quickly tell you how to know that a chemical reaction is in equilibrium. When you calculate your Gibbs free energy and your change in Gibbs free energy gives you 0, that is a reaction in equilibrium. Remember also that if your change in Gibbs free energy gives you a negative value, that is a system that is a reaction that is going to be spontaneous. Okay, so that's why you see that Gibbs free energy tells us about the feasibility or more like spontaneity of a reaction. Okay, so basically when it is negative, the reaction is spontaneous. Spontaneous means that it can happen on its own, okay, without any external influence. Then there's change in, if the change in Gibbs free energy gives you positive, then the reaction is non-spontaneous. So what does non-spontaneous mean? Non-spontaneous means non-feasible. It says spontaneous is feasible, so non-spontaneous will mean non-feasible. That is, it cannot happen on its own except there is an external impetus. Now, you see that these values, this Gibbs free energy may not be what to be given. They could also give you the electrode, the cell potential, the cell potential, yes, or electrode potential. If the cell potential is 0, reaction equilibrium. If the cell potential is now negative, if cell potential is negative, it is the opposite. It is non-spontaneous. If the cell potential is negative, it is what? Non-spontaneous. But if Gibbs free energy is negative, it is spontaneous. So don't forget that. While if the cell potential were positive, then the reaction is spontaneous. The reaction is spontaneous. Right. So that's just a side note. Now let's get to business. What I mean by spontaneity and non-spontaneity is like this. See, this is the locus classicus I give. For example, if I have a ball here, which of these will the ball naturally do? Maybe there are two balls. We have ball A here and ball B here. So this ball A, which of these will naturally happen? A, ball A rolling down to meet ball E, or ball B rolling up to meet ball A. Which one will naturally happen? The one that would naturally happen unassisted is ball A rolling downhill, right? So that is spontaneous. You don't need anything to cause that to happen. But for this ball B to come up to ball A, you need an impetus. For example, you could impact force by kicking, by throwing, or whatever you. So that is spontaneity and non-spontaneity. So when a reaction like this goes, so for example, this ball rolling down is spontaneous reaction. This ball rolling up is non-spontaneous, requires what external impetus, for which the Gibbs free energy will be positive and spontaneous, the Gibbs free energy will be negative. But E cell, the Gibbs free energy, if the E cell is negative, that reaction is not spontaneous. If the E cell is positive, that reaction is spontaneous. All right, so let's go on now. Let's go on. I hope you now understand that. Now let's quickly talk about two types of, no, before we talk about two types of reaction, there's what we call equilibrium constant, Kc. The way we write it is the product of the concentration, depending on what you're writing on based on concentration, so we'll call that Kc, equilibrium constant for concentration, and also have equilibrium constant for pressure. So concentration equilibrium constant is written like this. If I want to write for this guy that I have here, if I have, for example, numbers, moles, that shows mole, if I have them here, that I'm putting as subscript A, subscript B, subscript C, subscript D here, the way we write it is that we write the concentration of the product over the concentration of the reactant. That is what equilibrium constant is. So in this case, what are we going to write? The product includes C plus C, right? So we'll write it this way. C, now it will be, C here will be raised to power of that mole, C. So that mole will be the power here times, or multiplied, not plus, please, multiplied by D raised to power D, all over A raised to A, and B raised to B. All right. I hope this is clear. So that is equilibrium constant. Now, the next thing I want to look at is now what is called the Le Chatelier's principle. I'm going to expound on this later. The Le Chatelier's principle. Now, Le Chatelier's principle states that when a system is in equilibrium, I'm going to state it. When a system is in equilibrium, the equilibrium tends to shift. Le Chatelier's principle says that when a system in equilibrium is acted upon by an external force or impetus, the equilibrium tends to shift so as to annul or cancel the effect of that impetus that is acting upon it. I'm going to state that again. The Chatelier's principle states that when a system is in equilibrium, the system is stable, is on its own, it's not disturbing anybody. You understand? And then an external force wants to come and disturb the system. What will happen is that the equilibrium will shift in such a way as to annul or abrogate or cancel the effect of the external impetus. Let me give you a good context of what I just said. So look at this marker on my hand now. So for example, this marker, if I stand it well here, this will be the center of gravity of this marker. If it stands like, you see that it's stable here, right? If I add a load, for example, to this point, what will you see? What are you seeing? You see that the marker is tilting in this direction, right? So in a chemical reaction, this pivot here, where it is being fixed here, this pivot is going to be like, think of it as the equilibrium, the one that is setting the equilibrium. So this pivot will shift in a direction. So for example, if I add this weight here, this equilibrium will shift to this direction such that it annuls the effect of that external force that has been added to this place. Is it clear? This pivot is going to shift to make sure that that effect of this thing is cancelled. Is it clear? Good. Now, quickly, let's talk about the factors that affect. We're almost done. So it's this one that students have problem with the most, and that's what I want to really address. Now, what are the factors that affect chemical equilibrium? There are three major factors. We have the temperature that we talk about, and the temperature. We have the concentration, and we have the pressure. Temperature, concentration, and pressure. Now, pressure affects gases only. Their concentration, those are the things you must first keep in mind. Now you see temperature is where we're going to start from. Now another one student confuses, they add catalyst now. You see, catalyst does not necessarily, what does a catalyst do first? Catalyst, see the word catalyst, let me tell you the meaning of the word. You see the word kata, C-A-T-A, when you see it begin a word, it means down. Kata means down. Okay, catalyst, it means down. So of course list means break, right? Break down. Actually, how I like my students to remember it is, if you remember your textbook where you were shown the energy profile of a chemical reaction, you see that if it starts from a particular amount of heat energy here, which is called enthalpy here, and this reaction actually proceeds right like this. If the reaction were catalyzed, what will happen is that it will start from here, but this time it will go via a lower energy profile. So what it does is that it brings down, so think of it, catalyst, brings down kata, that is down, okay? Catabolic, all those words, kata means down. So it brings down the energy profile. The amount of energy required will not be much again. Do you understand now? Good. So, but what is the effect on chemical equilibrium? Catalyst does not necessarily affect the chemical equilibrium. What it does is that it speeds up the rate at which equilibrium is approached. Is it clear? So it means that when you catalyze a reaction, that should be a reaction, and the reaction is to attain equilibrium, the equilibrium will be attained faster. Is it clear now? All right. Now let's go to temperature. Now before we discuss temperature, you have to understand what is called enthalpy change. Enthalpy. Enthalpy is just another word. Think of it as another word for heat. Actually, it's not exactly heat, okay? It's not just heat, okay? But heat is a little bit, heat energy actually has more to it than just enthalpy, okay? Okay, so, but it is denoted by H, so we call delta H, that is change in heat of the reaction. Now, there are two types of reaction. I want to explain temperature now, listen. There are two types of reaction based on enthalpy change. We have the endothermic and we have the exothermic reactions. Now the endothermic, endo means inside, therm, whenever you hear the word endo, it means inside, right? But the word therm, from the word therm or therm, yes, threme, means heat. Means what? Heat. The Latin will be, I think, thermos or something. So it means heat. So whenever you hear therm, it means heat. For example, thermometer, measure of hotness or coldness, right? And it's used to measure how cold or hot something is, right? Thermometer. Then endo, inside. So look at it. Endo, therm, it means that heat inside. Does that make sense? So if heat is going inside, where is it coming from? It's coming from the environment. Okay, so in order to understand that, you have to understand the systems of the universe. There are three systems in the universe. We have the open system, the closed system, and the open system, closed system, and the isolated system. Now let me explain something to you. So there is a system and there is the surrounding. So there is within the system and there is something inside it. So for example, if I pour water inside a glass cup, for example, that cup is the surrounding of the water. Is that clear? The water is the system, the cup is the surrounding. Is it clear now? So I am saying that, so there is surrounding and the system. So a system is called open if the system, so what I'm trying to first say is that if I have a system and the surrounding, both of them are they relate to one another, okay? They exchange things, they relate to one another in one way or the other. So an open system is one that exchanges both matter and energy with its external environment, while a closed system is one that exchanges energy only, energy but not matter, While an isolated system exchanges neither energy nor matter. It doesn't exchange anyone with the environment. Okay, so that tells you that everything in an isolated system is what is conserved. So actually, isolated system is hypothetical. No, not hypothetical. Is kind of in the ideal case. Okay, it's a case of idealism. Now I don't know if there is isolated system in the world, because you cannot primarily totally isolate a system. Okay, so but isolated system is seen in the context of, if it were possible that we could isolate a system, what would happen is that energy will not be exchanged or matter exchanged with the environment. But in a closed system, energy is exchanged, matter and energy is exchanged in open system. I'm going to give you what these are in the context I want you to think about them. So endotherm is the one that collects heat. Think of it that way. That collects it from the surrounding. In as much as you see this endotherm, it reminds you that the heat is going inside. That is, the inside will be hot. Think of it that way. The inside will be hot. Now, heat and temperature are different, okay? Temperature is our perception of heat. Is that clear? Temperature is energy. Heat is energy. Temperature is human perception of the amount of energy locked up in the system. Make sense? So I am saying now that endo is inside, therm is heat. So heat is going inside. So where will the heat be coming from? From the surrounding. Then an exothermic reaction or exothermic system is where heat is going out of the system. That is, the surrounding will be warmer than the surrounding was not warm initially, but immediately you introduce that thing, the surrounding will become warm. That is, the system is losing energy, heat energy in this case, to the environment. All right. Since we already understand this, let me quickly give us a good context of this open, closed, and isolated system. Think of a pressure pot, right? Your ordinary pot and your pressure pot. So between both of them, which one cooks faster? So we know that the pressure pot uses the principle of Gay-Lussac, but I like to use it to explain this system too. So I don't want to look at it in the context of pressure now, pressure being another of those things. No, I want to look at it in the context of what it exchanges. If you use your normal pot to cook rice, for example, okay, what you will notice is that after a while, the rice, the molecules of water and the rice, they will be fighting. Yes, and you just see blood everywhere inside your pot. You'll be fighting, and in fact, if you had ever because there was one time I was cooking rice like that, and I saw the pot, the lid of the pot, I saw it jumping up and down and jumping up and down. I needed to go inside and go and check what was happening. The moment I got into the land of the rice, I saw everybody was fighting. They shouted, they even pushed me out there. They said, Master, don't worry. Master, meet here first. Do you understand? Everybody is just fighting. Okay, so you see the lead, even the lead will be jumping up and down, and you see heat going out, right? Vapor, water vapor will be escaping. So that water vapor is matter, makes sense? Then it carries with it heat too, right? So that is matter and energy being exchanged. So in that pot, even though your pot is not opened, it's not totally closed either. So we see it as an open system. Do you understand now? So that's why we're calling it an open system. Now, why does a pressure pot cook faster? I'm going to explain now. In a pressure pot, you notice that the degree of randomness is conserved, not just conserved. That randomness, and I don't want to use the degree of randomness again. That's another term. That's entropy. But the point is that chaos that is happening inside, that discombobulation happening inside the pot, is conserved. There's not much heat being lost. There's not much. You see that in your pressure pot, your pot does not dance around, right? The pot is locked. The lid is locked. Do you understand? So because of that system does not have so much matter to lose or energy to lose with matter. Do you understand? Because energy is locked up in matter. So once the water vapor were escaping from your ordinary pot, it also went along with some energy. So that's why your pressure pot will cook faster, because the energy is conserved within the system, and matter is quite conserved, even though some are still lost because it's not a perfect system, of course, but you can look at it as in the context of closed. Is it clear now? So notice that if you opened your pots downstairs, it will take longer to cook. You will never see them fight. You understand? Because they are shy. But when you lock them up, they will fight. Yes, and you increase the temperature of the heat. All right. I hope you got that. That's what I just explained. Now, so listen very carefully. Now, for an endothermic reaction, the change in enthalpy is positive. So when you see a number given to you, you see delta H, and you see positive in your answer, and you see a positive number in front of it, then that reaction is endothermic. If you see delta H given as a negative value, given with a negative value, then that reaction is what? Exothermic. I'm going to explain what that means in context. Endothermic has enthalpy change of positive. So what that means is that if I write a reaction like this, CO plus O2 to give CO2, for example, and I tell you that the change in enthalpy now, this is hypothetical. I can't remember the change in enthalpy, but I am just giving you an example. So for example, if I were to give you that the change in enthalpy of this guy is 20 kilojoules per mole, for example. Now, is this positive or negative? This is positive, 20 kilojoules per mole. That's the unit of enthalpy. But we're not dealing with that today. I'm going to deal with that in energetics. Now, I said that if this guy is given as equal to 20 kilojoules per mole, is this positive or negative? This is positive. If it were negative, you would have seen a negative value here, a negative sign here rather. So since this is positive, I ask you, is this reaction endothermic or exothermic? This reaction is endothermic. What that means in context, listen to me. What that means is that this reaction will naturally proceed forward by a what? By an increase in heat energy. I don't want to say increase in temperature, but that's the best way to think of it, okay? That's at least, that's the best way to think of it. Think of it as an increase in temperature, okay? Because that's your perception of heat. But actually what this means is that this reaction will naturally proceed forward by an increase in temperature, by an increase in heat energy. All right. That reaction is not balanced, so you can do well to balance it yourself. I think we just need half here. So it becomes, to put 2 here, multiply through by 2 and all those things. All right. But the point is, that's what this means, okay? I want you to understand equilibrium positions now with respect to temperature effect, concentration effect, and pressure. So first understand that these things I'm explaining now. When delta H is positive, the reaction is endothermic. Delta H negative, reaction is what? Exothermic. If I told you that this reaction is that the change in enthalpy is minus 20 kilojoules per mole, what this means is that this reaction will naturally proceed forward by a decrease in heat energy or a decrease in temperature, the best way to think of it. This reaction, if it's negative 20, negative number that you're seeing there, it means it proceeds forward naturally by a decrease in temperature. So what does that mean? It means that, listen. It means that since this guy is negative and it means it's proceeding forward with a decrease in temperature. If I go and increase the temperature of this thing, where will it proceed? It will proceed where? Backwards. Is that clear now? So when you write a chemical reaction and you are seeing this negative as the change in enthalpy, it means it proceeds forward, because forward is our normal reaction, okay? So if it means this reaction proceeds forward by an increase in temperature, by a decrease, this is negative, a decrease in temperature. If you increase the temperature, what would happen? It would proceed, it will go backward, recede, not proceed, to recede. Exactly, to go to favor the backward reaction. I'm already using the terminology we are going to use under this equilibrium now. Okay? So that's that. Now there is one other law that you should also know. Hess's law. Okay? Hess's law. Now Hess's law simply says that whether a reaction proceeds in one step, in a single step, or multiple steps, the enthalpy change is constant. The enthalpy change does not depend on the route it takes. If it goes on in multiple steps, that is, if it forms something, an intermediate or another intermediate and another intermediate before it forms the final product, it doesn't determine whether it doesn't affect the value of the enthalpy. Is that okay? It doesn't affect the value of the enthalpy. And enthalpy is stoichiometric in function. Stoichiometric in the sense that if this value goes on like this, it means that 1 mole of this requires half mole of this to give you 1 mole of this, right? If I double this, if I put 4 here as my number of mole, I need 2 here. Is that right? And what will I produce? I will produce 2. By the time I double that, because that is now in the 4th ratio now, it means that I will quadruple this guy here, this thing. But watch out for a video on energetics. The one you are most likely to see are the ones I'm trying to explain now in chemical equilibrium. But we'll get energetics. I will do that Hell's law in energetics. Okay. Now, what is the effect of temperature? Now, there are 3 statements we use. We use, if the reaction favors forward reaction, we say forward reaction is favored. Let me write it. The 3 statements we use. Forward reaction is favored. Now we're talking about equilibrium now, so let me change this symbol to equilibrium sign here. Forward reaction is favored. Equilibrium shifts to the left, where's forward? Is forward right or left? That's right. So equilibrium shifts to the right, and more products is formed. More products are formed. Let's use plural. Are formed. Now listen. Usually here, if you know your product, you can easily write more. For example, in this case, it's CO2, carbon dioxide. More carbon dioxide is formed. Now, these are the 3 statements we use. Now, you now ask, this is for a case where forward reaction is favored. In the case where backward reaction is favored, you say backward reaction is favored, equilibrium shifts to the left, more reactants are formed. But it can never happen that you favor backward reaction and now shift equilibrium to the right. Once forward reaction is favored, equilibrium has definitely shifted to the right and more product has been what? Formed. Is it clear? You cannot have them, they cannot negate each other. If you say equilibrium shifts to the left, then you are trying to say that more reactant is formed, and you're also trying to say that equilibrium, you say equilibrium shift to the right, you are trying to say that backward reaction is favored. So these are the 3 statements we use. So now let's get to it now. We're almost there. Or we are starting it now. So look at this chemical reaction. What kind of reaction is this? If I say, what is the effect? Now, what is the effect of increase in temperature for this guy, for this system here? I just wrote. What's the effect of increase in temperature on this chemical reaction? Now, I'm going to write the 3 things that will happen. So the first thing you observe is there is delta H. Once there is delta H there, temperature affects. So that's the first thing to look out for. If there's no delta H there, temperature does not affect. So that's the point. Now, there's delta H there, temperature affects. So now what's the delta H value? It is negative. That delta H is negative. What does that tell you? The reaction is what? Exothermic. What does that mean in context? I told you, it means that the reaction naturally proceeds forward by a decrease in temperature. So we now know where the reaction naturally proceeds. It forms CO2 by a decrease in temperature. What will now happen if we go and increase the temperature? What will happen? You already know the answer. It's going to what? Favor the backward reaction. So you say backward reaction is favored. Backward reaction is favored. Then equilibrium shifts to the left. Equilibrium shifts leftward and more reactants formed. Is that okay? MRF means more reactants formed. Is it clear? In this case, which reactant are we talking about? Carbon monoxide and oxygen. Okay? But then you might now ask me, which of them will be formed more? I'm going to deal with that in concentration. Okay? I'm going to deal with that in concentration. So what if this reaction were to be positive? And I say I increase the temperature the same way. You know that when the reaction is positive, the enthalpy change is positive rather. It therefore means that the reaction is endothermic. Once it's endothermic, then you know that it naturally proceeds forward by an increase in internal energy, in temperature, for example. So if that's the case, you now increase temperature, what will happen? It means you are favoring forward reaction, more product formation, and equilibrium shifting to the right. Is it clear? Good. Good. Now let's get to temperature. You see, we're almost ending it now. We're wrapping it up now. Now, concentration is very important. Now, listen carefully. Listen carefully. Listen carefully. All right, let's go. So I have concentration. Concentration. Now, what is the effect of concentration in a chemical reaction? Now, first, listen. Concentration only affects, concentration has to do with the amount of substance. Think of it that way. It is the amount of substance there. Now, when you increase concentration of something, the substance that will be favored will be the substance that is less. I'm going to repeat that. So we have reactant, we have product. So this is the way it is. If you increase concentration of reactant, it means that we have less product there, right? If you keep adding reactant and adding reactant and adding reactant, it means the product is less, right? So because of that, we will form more product. So we always form more of what is less. Is it clear? So if in a chemical reaction I decide to increase the amount of product I have, I'm adding to the product and adding to the product, what will happen? It will reverse. So once the reaction reverses, it means it will now be favoring the formation of the reactant again. Is it clear? So for example, I have this reaction, this chemical reaction. Let's say, let's use the classical example like ClO3. So you have CkCl plus O2. Okay. I can't remember if this is an equivalent reaction, but I can't remember. But let's just take it as an example. So as it is, if I increase the concentration of this guy, what and what will be formed? More and more of this or this will be formed. Is it clear? More and more of this product will be formed, because the more of this I add, the less of this I have. The more of this product reactant I have, the more of this reactant I add, the less of the product I have. So for which reason, more products will be formed. But in a case where I now decide to do this, watch. If I now decide to now add more and more KCl, as this reaction has been set up, I now decide to add more and more KCl, more and more KCl, more and more KCl. What will happen is that potassium chloride that is being added here is going to be more. Because it's more, it will make the product less. And for which reason, it will make the reactant rather less. For which reason the reactant will be what? Favored. The formation of the reactant will be what? Favored. So we are saying that equilibrium, if I keep adding KCl and more KCl and more KCl to favor leftward reaction, or equilibrium will shift to the left, favor backward reaction, and more reactant is formed. Why? Because I'm adding more and more of this. For which reason I'm having less and less of this. Is it clear? Now there is something also. Now this is where students get confused. A question will now say, if as this KCl, potassium chloride is being formed, I keep removing it. Then the question now says, which of this is the case? Now let me ask you, what will happen if I keep removing this? If as this thing is being formed, if I'm removing it, if I'm removing the product as it's being formed, it means I keep having less and less of the product. So I'm having less and less of the product as I'm removing the product. So it means I'll keep forming the product. Is it correct? So the equilibrium will keep shifting to the right. Keep in mind, the side that is less is the side that will be favored. Is it clear? All right. All right. So that's concentration for you. Let's go to pressure. Now, keep in mind, pressure only deals with gases. So if you have a chemical reaction and you have the subscripts, you check the subscripts and there's no gas there, and they ask you what's the effect of gas, what's the effect of pressure, increase or decrease in pressure, you say null, no effect at all. Is it clear? All right. So now, keep in mind also, let me give you a classical example, like process of formation of ammonia, Haber-Fried's process. Okay, so looking at this reaction, keep in mind the following. Okay, I didn't even write the equilibrium constant of pressure. Keep in mind the following, that, listen, that an increase in pressure favors the side with lower number of moles, with lower volume. You know, the volume, the moles also dictates the volume. With lower volume or number of moles. So it's the side that has low mole that increase in pressure favors. But it means therefore that a decrease in pressure will favor where? Favors where? Favors the side with higher number of moles. Is it clear? So easily, in this case, let's count. What's the total mole in this reaction? Here we have 1 here, 1 mole here. Is this reaction balanced? Yes, it is balanced. Okay, so we have 1 here, we have 3 here. That's 4 moles altogether. Then on this side, we have just 2 moles. So keep in mind that I counted the moles of the 2 reactants together to give me 4. So these reactants have more volume or more mole. Is that clear? So 4 moles here, 2 moles here. And I ask you, what is the effect of temperature on this thing? If there is no change in enthalpy, we have null. But I now ask you, what is the effect of increase in pressure? What will happen if I increase pressure for this reaction? Remember, if there is an increase in pressure, the side with the lower number of moles of volume will be favored. Now, which of these sides, is it product or reactant that has lower number of moles? The product, of course, it has 2. So which side will be favored? Product formation. So forward reaction is favored, equilibrium shift to the right, more product or ammonia is formed. Is it clear? But if I decrease pressure, which side will be favored here? If I decrease pressure, remember, a decrease in pressure favors the side with higher number of moles. So which side is higher number of moles? The reactant side. So equilibrium shift to the left, backward reaction is favored and more reactant is formed. And that is all about that you need to know for this short video. So when I release my video on energetics, if you do anticipate it, put it in the comment section that you anticipate it so that I can make the video on time, because there are also other demands for other videos. So I'll prioritize it when I see your comment. Alright, so do want to subscribe to the channel, share the videos with your friend, the video with your friends, and God bless you as you do so.